presentation will be available on the CESTiCC website after this webinar ends. Our speaker today is Xianming from the Washington State University, who has been funded through CESTiCC to do a number of different projects. And the one he's discussing today is the Deicer corrosion to DOT equipment and vehicles, best practices in prevention and mitigation. If anyone needs to get credit for attending this webinar, please send an email after, and I will provide the continuing education credit certificates. And with that, Dr. Shi, take it away.
All right, thank you so much, and welcome to this webinar. Good morning, I guess some folks are good afternoon, and this is actually, you know, a presentation I was invited to give at UC Davis a month ago, but I figured probably for the broader audience, this might be helpful. So again, the title is Deicer corrosion to DOT equipment and vehicles, best practices in prevention and mitigation, and my collaborator is Mehdi Nazari. He's also pursuing his second PhD with me right now. So the talk will cover, you know, the following topics, stuff from introduction of the topic, and then a little bit discussion of, you know, the role of chloride-based deicers, how they influence the corrosion of metals, and then move on to corrosion mitigation strategies with a focus on preventive maintenance or preventive methods, and then conclude with some key findings and research needs and acknowledgements. So to start with the bigger picture, here's the emerging, a list of emerging challenges for the transportation agencies. Basically, they are having a tough time trying to meet multiple priorities, such as safety, mobility, level of service, and then on top of that, you know, today we're talking about minimize corrosion to metals, and then there's also environmental stewardship, you know, in terms of impacts of such operations to water quality, soil, vegetation, air quality, even wildlife habitat. So it's a very difficult task, and you know, what's even more challenging is they're having to deal with increased traffic volumes, higher customer demands in recent years, and also funding, staffing, and technology constraints. So I would argue that the only way out is to use the best possible science and technology and practices to find the solution for this cross-cutting issue. So at the bottom, I sometimes list a few papers we published relevant to the topic. You know, if you're interested, you can always look further. You know, the context is such that the deicers are increasingly used for winter roadway operations, and right now we're dealing with roughly 20 million tons per year on US roads. Of course, that includes not only highways, but also local roads. And typically these deicer products, they contain some chloride-based salts to serve as freezing point depressants, you know, sodium chloride, which is the table salt we eat every day, and also this magnesium chloride, calcium chloride. So the estimated damage to the motor vehicles every year is $2.8 billion. Now that includes mostly, of course, the traveler vehicles, but also DOT vehicles. Now, when it comes to DOT, because some of the vehicles are used for winter operations, they're exposed a lot more to such corrosive chemicals. And in the vehicles nowadays, we have all sorts of metals, you know, carbon steel, cast iron, aluminum alloys, magnesium alloys, copper alloys, and so on. Of course, even increasingly so, stainless steel has been used. So, so DOTs are certainly seeing some apparent signs of corrosion, and their vehicles design life typically say 15 years, now it's reduced to 10 or 12 years, and a fraction of that cost due to corrosion, you know, roughly estimated 25 to 30% could be preventable. In other words, the majority of the cost is not preventable because corrosion is such a natural tendency for metals to oxidize and corrode. In order to prevent or minimize this risk, we need investments on the maintenance programs. So another issue complicating this risk is localized corrosion. In other words, if the metal is corroding at a uniform rate and highly predictable, then we can select the right materials to manage this risk. However, oftentimes the corrosion is highly localized, and there are many, many forms of localized corrosion. You know, if you're a corrosion scientist, you know this. But you know, there's a whole list. You know, pitting corrosion, crevice corrosion, filiform corrosion, intergranular corrosion, galvanic corrosion, stress corrosion cracking, corrosion fatigue, threading corrosion, microbial influence corrosion. Some of those are not just the corrosion itself, but also in conjunction with mechanical stresses or you know, microbe actions and so on. So that makes it really difficult to predict or prevent. So you end up with unexpected failures and more frequent inspection and maintenance just to manage the risk. For instance, a recent field trip we had to a trucking company in Butte, Montana. You see this kind of phenomenon known as rust jacking, a form of basically corrosion fatigue. Because of the design, you know, this is a double frame, and the corrosion product, or the rust in this case, is kind of stuck in the middle, and then because of the expansion of the corrosion rust or product, you got this so-called rust jacking, basically the cyclic mechanic stress induced by this rusting process, and that makes the situation much worse. So we had a few different cases, you know, like this one, and there's another one with the brake shoes, which is even more concerning because of the safety implications. If the brake fails, then that's even more than just you know, cost issues. So a national survey we did back in probably 2013, you know, reached to dozens of agencies, and the survey basically identified the corrosion-prone parts. The most vulnerable ones were electrical wiring, frames and brackets and supports and so on. And then also we have a list of the ones which will induce higher repair costs, like the chassis, the axles, the brakes, and so on. So of course that was kind of a snapshot out of a larger population, you know. But that survey also helped us to identify, you know, what are the current practices or best practices and the cost implications and so on. For instance, that helped us to answer this question: how much do agencies currently spend on corrosion management? Here we're mostly targeting northern transportation agencies, and according to the survey, the average was these numbers, you know, in different categories, totaling around $1 million. Of course, some agencies spend less or some spend more, but you can see that right now they're not spending a whole lot on proactive maintenance. You know, instead they're spending more on reactive maintenance. And when it comes to material selection and design improvement, we'll talk about later. You know, certainly there's room for improvement, and there are people making a career out of these things. You know, just select the right materials for the right service environments. So we actually run a preliminary cost-benefit analysis, applying some assumptions, and based on the survey results, we assume that it's possible to conduct risk analysis to identify the most critical 20% of the corrosion-related failures, and also in terms of solutions, focus on the most fruitful ones, such as training and risk-based maintenance. In that case, we can come up with a benefit to cost ratio 13.2. So that's saying that right now we're spending roughly $1 million on corrosion management of vehicles. If we can bump up that by 20%, we probably will achieve, you know, a significant cost savings on corrosion. And here we have a number 25%, assuming that only 25% of the corrosion costs are preventable. But right now, you can see the average cost is $14 million per northern agency. So that's how we run the preliminary analysis. Of course, this was not perfect, but a first step towards the right direction. Well, to reiterate this. Basically, if we're spending $1,000 on corrosion management, we could gain, $13,000 in return. Now, moving on to the role of chloride-based deices, as we mentioned, especially with roadway deices, most of them contain chloride salts. So one detrimental effect is that the chlorides tend to absorb water even at low humidity. So you can see here for rock salts or your typical sodium chloride, the threshold is 76% relative humidity. That means if the surface environment is somewhat humid, you have 76% humidity, then that metal surface will be kept chemically wet, and that will basically enable the corrosion. Now, in the case of magnesium chloride, it's even more concerning because that threshold drops to 35%. So, in other words, it can mostly keep the metal surface chemically wet, and once you extend the time of wetness on the metal surface, basically that enables a lot more corrosion. Now, the second mechanism by which the chloride salts accelerate the corrosion risk is to increase the conductivity of water. Once the conductivity of water is increased, the rate of corrosion propagation increases. So a third one is the chloride ions actually serve as a catalyst for the metallic corrosion, and I'll explain what that means. And also, this type of corrosion induced by chloride tends to be in a highly localized fashion. So on the metal surface, usually you have some sort of oxide, hydroxide layer, very thin, ultra thin layer. But that passive layer, which is supposed to be protective, could be disrupted by the presence of chloride. Now, for instance, some of these typical chemical reactions or electrochemical reactions, the iron oxides itself turn into rust, but the chloride basically facilitates that process. And you can see on the top, chloride being consumed, and the bottom chloride being regenerated. That means the chloride is a catalyst. It's not being consumed, but it facilitates the reaction thermodynamically and also kinetically, make it much worse. In terms of localized fashion, when you have rust, for instance, under rust, you could form a highly localized condition, which tends to be really rich in chloride ions and also tend to be more acidic than usual. And that basically further accelerates the corrosion. Again, the localized corrosion is much more problematic than the general corrosion, or also known as uniform corrosion. So in other words, it's hard to just say, hey, if I know it's corroding at 1 quarter inch per 5 years, let's just design it to be thicker. That really doesn't work in this kind of scenarios, because the localized corrosion rate at that spot usually is 5-10 times faster than usual. And also it's hard to predict. Now, to illustrate the unusual situation with magnesium chloride, we mentioned, its so-called deliquescence point, or the relative humidity required to maintain chemical wet is really low, 35% relative humidity. So we had this field testing in Montana and simulated the situation. We had a automated sprayer periodically spraying the magnesium chloride 20% magnesium chloride solution onto these coupons, and some are stressed, some are not externally stressed. So what we saw is that for the aluminum alloy here, even though we don't see much rust on the surface, it looks still somewhat shiny. But in fact, when we test the tensile strength, there's a loss of 35% tensile strength. And in the case of carbon steel and the two stainless steel groups, we're actually seeing less reduction in tensile strength, even though the carbon steel looked really, really rusty. So what's that telling us is basically what you see can mislead you. The strength loss could be entirely different than the trend you see in mass loss or percent rusty area. So don't trust your naked eyes too much, I guess, in this case. It's kind of interesting anecdotal that we also happen to be the ones doing a study for Oregon DOT on Portland, gas impact on Portland cement concrete. And the phenomenon there was very similar. For the concrete exposed to magnesium chloride, we don't see much surface distress at all, no scaling whatsoever. So with traditional visual inspection, it would rank it 9 out of 10, for that bridge deck. But when we actually test the splitting tensile strength in that case, we often see like 30 or 40% loss. Of course, that was after, a decade or so exposure to concentrated magnesium chloride solutions. But anyways, these things are kind of concerning because our traditional inspection methods no longer work. Now, to further illustrate this point, you see some micrographs done by the so-called scanning electron microscope. Here, each photo basically is really, really small. On the left-hand side, for instance, you have a bar showing 20 microns. To relate to that, your hair size typically is 80 microns in diameter. So this is roughly the size of your hair. On that surface, you see on the top group is stainless steel 304. The bottom is aluminum alloy 1100. Now, after exposure to magnesium chloride, basically, you can see that even the stainless steel has some, corrosion. Again, stainless steel is not really stainless, depends on the situation. Now, for aluminum, the situation is much worse. So basically, what we found with this surface morphology and also some chemical analysis with the advanced tool, basically we found the mag and chloride ions penetrate really, really deep into the aluminum alloy. So that explains why earlier, even though we don't see much surface rust, but we saw a significant reduction in tensile strength. Now for carbon steel, even though it's not shown here, basically we saw pitting on the surface, but we don't see a whole lot of penetration of mag and chloride ions. So it's very different mechanism. So in the case of aluminum alloy, we suspect it's intergranular corrosion. Basically, the corrosion propagates through the grain boundaries of the metal. Now, sort of armed with that knowledge, we move on to countermeasures or corrosion mitigation strategies. The first thing is always the solution in the management domain, which is not even in the technical domain. So good training is important, good facility management is important. For instance, the US DOT has been fighting this battle for much longer. Of course, they have a lot more budget to deal with this issue. So they have much more well-established process. This here just shows one example. They have a flow of tasks for managing corrosion, the defense equipment assets. They have different teams look at different stage of the corrosion issue. So maybe transportation agencies could learn a few things from their process. Now, if we move on to the technical domain, the first group commonly uses so-called reactive methods. Basically, once you have corrosion, what do we do? Agencies tend to replace damaged components, which is costly, and also sometimes we use rust converters, trying to at least slow down the situation and make the rust stop. And also there are other corrective maintenance activities such as washing or putting on some chemicals to slow down the corrosion. Now, like I mentioned earlier, actually agencies are better off if they focus on the preventive methods, just like in many other domains of preservation, whether it's bridge or pavement, the same deal. If you spend $1 million this year, you could, prevent or avoid a corrosion cost down the road, probably $5–6 million. So in that category, the first few are material selection, design improvements, and anti-corrosion coatings. So these things can be specified in the equipment specification so that, starting from new equipment, it can be built to last longer. Now, if we pass that stage, we could do a few other things like washing and the use of soft removers, the use of corrosion inhibitors, and the use of agricultural-based materials for snide control, which is basically less corrosive deices. I'll go over each one of these a little bit. So starting from material selection, again, we probably don't need to go through the entire list. Basically, the industry, especially with associations such as National Association of Corrosion Engineers or NACE International, and also the Society for Protective Coatings, over the years, both the practitioners and researchers have accumulated some knowledge. So knowing that what type of material would fail or survive under certain conditions. So as you can see here, like I mentioned, even stainless steel won't work in some scenarios. So we better know what type of stainless steel we're dealing with and what type of risk, in that environment. For instance, the use of magnesium chloride deicer is a newer challenge than the traditional rock salt. Now, with the use of beet juice and other agricultural byproducts, there may be additional risks, especially some of them are difficult to wash off the vehicle. So again, the details are provided here so that if you look at the slides later, you can gain some information. But I won't go into the details because again, for material selection, this actually is a big industry. There are software applications available and also experts focused on material selection. Now, a few interesting examples from the field, people have had success. For instance, like the first one, they changed the fuel tank to aluminum and seem to last longer. But now I'm getting concerned if they're constantly exposed to magnesium chloride environment. As you saw earlier, even if they look fine, no rust, maybe the strength is compromised over time. And also you see changing of the hydraulic pipes from carbon steel to stainless steel, it looks a lot better. And also the use of some fender guards to fend off some of the spatters from, the splash from the roadway, help protect the vehicle. So there are a lot of different scenarios, like this E-coated frame rail would last longer than the one without the coating. Some of the coating at the bottom, underbody of the vehicle actually needs to be more like abrasion resistant and also self-healing. Now, the second tool in the toolbox is really design improvements. Again, the corrosion industry has accumulated a ton of knowledge on this. Some of that, actually most of that, could be applicable to the vehicle design. For instance, importance of drainage. We don't want to keep the vehicle wet, even if it's chemically wet. So if we can drain most of the water and avoid any accumulation of moisture, especially in crevices or hidden areas, that's better. And also, sometimes the design is not with the corrosion prevention in mind. So you could have sharp corners that makes the application of protect coatings difficult. And also in other cases, maybe you have stress concentration. Again, if you have defects, stress concentration, or welded areas, usually that's where the trouble begins. Usually those areas tend to serve as local anodes that start to oxidize and produce electrons, and the surrounding areas become local cathodes. So basically you're forming a battery on that same surface, even though supposedly the same material, but because certain areas are more stressed, then they tend to behave differently. Again, the welded areas, I have some additional slides in the end, which will be included. Basically, there are a lot more details in terms of how you deal with the welded joints and so on. Now, galvanic corrosion is a big deal. You may be familiar with the theory of cathode protection. Basically, if you hook up two metals that are dissimilar in each other, then one will corrode as the anode and produce electrons. Those electrons are being pumped to the other one. For instance, if you have a carbon steel electrically connected to stainless steel, what will happen is basically the carbon steel will corrode a lot faster than without the electrical connectivity to the stainless steel. Basically, it's pumping electrons to protect the stainless steel, which doesn't need any protection. It's a very interesting case. So therefore, in design, we try to avoid this kind of scenarios. Worst case, if it's not avoidable, then we should coat both of them. And the other thing is, if coating is not possible, we should make the anode a lot larger than the cathode. Of course, you may have a scenario with the tank, like the vehicle may have a fuel tank with a stainless steel, body and maybe some carbon steel bond. In this case, because the stainless steel is rarely exposed to the corrosive agent, it may be okay. So it depends on the specific scenario. In other words, the metal which is not exposed to that liquid is safe. But anyways, the galvanic corrosion is a significant risk. Now, the use of some of the coatings would be helpful, especially the so-called active coatings such as zinc-rich primer Now, this is actually flipping the theory of cathode protection to our benefit. Basically, because of zinc in the coating is a sacrificial anode, it tends to oxidize easier than steel. So it will sacrifice itself and pump a lot of electrons towards the steel, make the steel corrosion resistant. Of course, in the state of Washington or in some areas, the potential release of that zinc into the storm water becomes another concern, environmental concern for fish species. Now, here's another case where one agency basically used stainless steel enclosure to protect all the operations, critical components. That's the best practice. We definitely recommend, because in the past, people have run into this issue. So now, the third tool in the toolbox is anti-corrosion coatings. Whenever we talk about coatings, of course, there's yet another huge industry out there. And there's also the Society for Protective Coatings, the NACE International. One lesson learned is definitely surface preparation is very important. Even if you have the best possible coating, but if you have very lousily prepared surface, that won't work. And here is a link to a document talking about CESTiCC, a lot of different protocols for how to prepare a good surface. Now, what we know about coatings, especially anti-corrosion coatings, they should be long-lasting, easy to apply, eco-friendly, cost-effective, and provide high performance, preferably also self-use. Now, eco-friendly could mean, there are VOC, volatile organic compound, is low or solvent-free. Oftentimes waterborne coatings are, getting into the market slowly. And also, again, we mentioned the importance of surface preparation. To assist with surface preparation, actually, there are some tools like the salt remover, which is designed to remove the residual salts, even if it's trace amount of salt from that surface, so that coating will last longer. But later, also, we talk about salt remover being used in the washing practice, so that we can, get the salt out of the crevices and the heating areas. And rust removers is yet another tool, and also yet another tool is rust converters. But again, here we mentioned in some scenarios, actually it's not desirable to use some of those tools. Now, here's another study we conducted which kind of shed some light on this issue. We had made this sensor, which is known as multi-electrode array sensors. This is in collaboration with Southwest Research Institute. They have this sensor. Basically, we made it out of steel, stainless steel, and aluminum alloy. And what we measure, continuously monitor, is the current, electrical current flowing between these sensors. So for each type of metal, we have 9 wire sensors. And we measure the average current and the maximum current. The maximum current flowing between them basically gives indication of the risk of localized corrosion. So in this scenario, we exposed these sensors to the diluted sodium chloride and the diluted magnesium chloride, assuming a 10-to-1 dilution, because sodium chloride usually, as a Deicer, is applied 23%, and nitride chloride is 30% by weight of solution. So afterwards, what we saw is this specific commercial coating protect the wires really well. So the currents we measured were, all the values were low, but we still see some blistering of the coating. Of course, this was accelerated testing in the lab, was highly demanding. And if we look into the 4th tool in toolbox, which is washing, and the recommendation to wash it daily. Of course, many agencies may not have the right facility, and also in certain areas, they're more concerned about the cost of compliance with the storm water or wash water treatment. So, but from the corrosion protection point of view, washing is very necessary, especially if you cannot afford daily washing, at least before the weather gets warmer, because that's when the corrosion really kicks off. So in this washing practice, based on a few studies, the best practices are such that You should use hot water that will basically wash it very quickly and get rid of the residual salt. And that's followed by fast drying because we don't want the surface to be either wet or chemically wet. And also, actually, we don't recommend high pressure washing, even though a lot of agencies are still doing that. Instead, we recommend high volume, high flow rate. So a typical example is 300 psi and 300 gallons per minute. But again, the concern is then what do you do with the wash water? Some agencies have tried to use that to make the salt brine, as well as the end product is in compliance with environmental regulations. That's a good practice. And also, there is a need to add salt removers, as we will demonstrate later, so that you can remove the residual salt in crevices. But the challenge depends on the specific product. They could be anodes specific. What we mean is that certain anodes may not benefit from this practice. So, there are a few best practices recommended from washing practice. Again, do not use a pressure washer because that could force salt actually into certain areas that cannot escape. And also the best practice, in our opinion, is to apply a spray-on corrosion inhibitor after the surface was washed and cleaned and dried, because that will extend the service life of that vehicle further. Now, one lab study we did is we used a patent process to derive some green chemicals out of waste sugar beet leaves. Now, this is different than the beet juice because in this case, this extract has this no sugar content. The organic content is much lower than the beet juice people have been using. Now, in this case, we found if blended with a 10% nitric chloride, we actually were able to form a protective layer on the metal surface. Now, this chart on the top, on the left-hand side, the R represents the corrosion resistance measured through an electrochemical method. Now, on the right-hand side, the only difference is power wash. So basically, before power washing, the corrosion resistance with this green additive is about 10 or even 50 times higher than the one without the the green additive. But once we power wash it, that benefit is gone. So power washing also has this potential side effect. Now, in terms of the use of salt removers, we also did another study. Again, some of these, coatings or salt removers we identified actually from the national survey, and then we further tested them in the lab. So in this case, basically, again, the y-axis is the corrosion resistance, and the x-axis is time. And these are accelerated tests, so the time frame was really short, 2 weeks. But we saw that the coupons washed with this salt remover in it tends to enhance the carbon steel and stainless steel resistance to nitric chloride. Usually lasts 9 to 10 days. But just wash it once, and then that benefit remained. But for the aluminum, the benefit was non-existent. And we confirmed that through the scanning electron microscope. Again, these are happening at a really microscopic level, basically finer than your hair. What you see on the left-hand side, very, very left-hand side, is the group washed by water. You see a lot of, pits or corrosion. On the right-hand side, however, you only see the one in the middle having some hole. The C and I were basically fine. So basically, in this case, when we wash it with HOTAT, which is a salt remover, in the wash water, then basically the carbon steel and stainless steel do not corrode as much. However, for the case of aluminum, as you can see, there's still a significant, very deep pit actually, because this salt remover did not help that scenario. Again, the corrosion mechanism is different there, most likely interparameter corrosion. Now, we also tried to wash with soapy water, which is the group in the middle. And you can see that it's a little bit, maybe slightly better than the washing with, tap water, but the benefits are really limited. Now, after washing, what we recommend is, you got a dry surface, now it's free of any sort of contaminants or residual salt. What you should do is spray a corrosion inhibitor. Spray on corrosion inhibitors. Basically, think about linseed oil. Basically, they're very similar mechanism. They're trying to make that surface used to be hydrophilic, likes water, and now turn into hydrophobic. So that surface will resist water ingress. So there are a lot of corrosion inhibitors out there. Again, starting from chemical engineering industry, there are many products out there. This has been studied, for decades. Now, the most effective ones, actually, especially from defense industry, that identify is chromate. Unfortunately, those things are highly toxic. So in recent years, there's more development of organic or inorganic inhibitors, which tend to serve as alternative to the toxic chromate inhibitors. And unfortunately for inhibitors, there's a certain critical concentration you need. In other words, if they're washed so much and diluted so much, then they lose their effectiveness. And also, the effectiveness is a function of the surface conditions. So that makes it difficult to find a good solution. There's no one size fits all. Now, again, from the previous accelerated lab test, we have this wire beam electrodes or multi-electrode array electrodes, the different names for it. But basically, again, the top group is exposed to diluted sodium chloride, the bottom groups are diluted magnesium chloride. In all these scenarios, the use of this corrosion inhibitor, a spray on known as Chrome T40. Again, the use of brand names are just for your information. We're not advocating any of the products. Actually, many of the commercial products under different names may share similar chemistry. So in this case, basically, the corrosion rate was reduced by at least 99% in all those scenarios. So it's highly effective. Now, the very last tool in the toolbox is the stuff on the root cause of the problem. Basically, what if we use non-corrosive Deices? Then we don't need to worry about the washing or other things, right? So again, like I mentioned earlier, we had one liquid chemical which is derived from waste sugar-beet leaves, and the organic content was low and the corrosion resistance was really high. But unfortunately, it's not very much resistant to the powder washing. And we used this approach, which actually the patent technology, to derive other green chemicals. The interest in this type of agricultural-based inhibitors is because there's research showing that they also may reduce freezing point of the Deicer solution, basically make the Deicer more powerful. That's highly desirable. And also they have a lot of other environmental benefits. Of course, they're from a renewable resource and they're biodegradable and everything else. They tend to feature this kind of molecular structure with some of these phosphates or sulfur or nitrogen or oxygen atoms. So these tend to absorb onto the metal surface easily and form a protective layer. So in this case, we developed a new process. The details are here, basically starting from chemical degradation and then followed by some almost you can consider as natural fermentation process at ambient temperature for 2 weeks. So, and then we used a tool known as liquid chromatography mass spectroscopy, or LCMS, to identify what kind of things are in this liquid chemical. Basically, it's a mixture, and the entire process generates no waste. Basically, we dump the entire thing into the Deicer solution. So from the waste peony leaves, we identified the main chemicals or active ingredients are these two types of organic phosphorus molecules, and they absorb onto the steel surface and block the cathodic active sites, basically make the degradation of water difficult. That slows down the corrosion process. And also they have the additional benefit of making the surface hydrophobic, so almost serve as a corrosion inhibitor mentioned earlier. And again, there are many other benefits like decreasing the surface free energy also makes the surface less likely to absorb water. And also they change the formation of the passive layer. Basically the passive layer was different, and even the Ross form was different. So it's very interesting. It's more than just a physical barrier. Now we adopted the same patent process to derive green chemicals from other feedstocks, such as apple pomace, the skin of apple. So we found the active ingredient in this case was a different organic phosphate. Using electrochemical methods, we were able to confirm that the corrosion resistance was increased significantly. In this case, the orange dots indicate that group with 3% this apple pomace extract, and then the blue one was without it. So this substantial difference, and the XY axis both indicate the polarization resistance related impedance. So the molecular structure, there are two main compounds working in this formula. The top one is, again, another organic phosphate molecule. So on one end, it's a fatty acid, so which is a tail expels all the water molecules, prevent them from attaching to the metal surface. On the other hand, there's a positive charge head which likes the metal, so will get easily adhered to the metal surface. So again, there are a number of tools we use to confirm that truly the corrosion behavior changed significantly with or without, the waste apple pomace extract. When blended at 3% by volume, it was the best. And after 2 weeks, what we saw, the corrosion rate basically reduced to close to 0. So we have corrosion inhibition efficiency of 100%. Now, but that doesn't mean it's a shiny surface. What actually happened is you're forming a very dense rust layer. Basically, no corrosion was possible anymore. So, so you can see on the very left-hand side, the figure A shows a partially covered orange rust, but on the very right-hand side, the D was a 3% waste apple pomace extract. In that case, basically, you form a uniform and complete rust. And this was confirmed by many different tools, like this one, electron probe microanalyzer, which is like a $1 million equipment. But what it does is to look at that very small area, much further than your hair, and examine what's going on. Here are the elements on the surface. You can see iron, or oxygen, chloride, nitrogen, and phosphorus. And basically, the phosphorus, the organic phosphorus molecule, was detected on the surface. So this helps the case. Basically, we mentioned, one end of that phosphorus molecule was hydrophobic, basically expels water molecules. And we also found that the rust formed was different, with or without this green chemical. Basically, in this case, with the green chemical, the rust was more oxidized and to a very uniform alpha and oxide layer. So the key findings from this apple pomace source inhibitor is that, all the things we mentioned, the electrochemical mechanism and also the rust was different, and the key active ingredient was an organic phosphate molecule. Now, that kind of concludes our discussion of best practice. There are many tools in the toolbox, but there are still a lot of knowledge gaps. So in terms of research needs, we have identified 2 of them, along with the translation agencies. One of them is the use of sacrificial coatings. Earlier I mentioned zinc-rich primer, but that's just one of the products in the series of products available. Whether or not they can really help with the case. Again, we mentioned some products may work really well, but they may have problems with blistering. Or earlier we mentioned underbody coating. We probably need to make it more abrasion resistant or even self-healing. Now, another topic is the use of cleaning strategies. Again, there's very little research in terms of what's the right pressure and flow rate to use for washing, and what type of salt removers, because we mentioned earlier, certain salt removers won't work for aluminum, and whether or not to spray on some corrosion inhibitor afterwards. So there are a lot of questions. One interesting practice by the Army is that after cleaning the vehicles, they would put them in dehumidified rooms so that it's constantly dry and the corrosion is minimized. To conclude, agencies should implement an extensive preventive maintenance program that may involve material selection, design improvements, anti-corrosion coatings, use of salt removers together with routine washing, spray-on corrosion inhibitors, and many other operational changes, which could be supplemented by corrective maintenance practices with the end goal reducing or minimizing the negative impact of corrosion, Deicer corrosion to equipment asset. To clarify, without Deicers, we still would experience corrosion, but the situation is much worse when we have vehicles exposed to Deicers. And I'd like to thank the sponsors for related research, Washington State DOT, Clearrose, National Science Foundation, and two of the UTCs, one of which is CESTiCC, and then Simpson Strong-Tie company in California, and a number of collaborators and students. And also a little bit infomercial here. We just published this first of its kind book called Sustainable Winter Road Operations, which talks about the multiple dimensions of this complex issue, and there are 20-some chapters written by the experts. And thank you for your attention. Now I'd like to welcome your questions.
All right, I'm going ahead and going to unmute everyone. If you don't have a question, please mute yourself again. All right, any questions for Dr. Shi?
Or do you have any types of questions from your end?
All right.
Hello.
Hi.
Hi.
Hi. So I have a couple of questions. This is Raghu Srinivasan here from the University of Alaska Anchorage.
Mm-hmm.
Yeah, so it was a really nice presentation. So I just moved up from Hawaii doing some corrosion experiments before, like atmospheric in general. It's kind of interesting to see it from a different perspective in terms of winter roads and then de-icing salts. I was kind of wondering, when I moved up here like 6 months ago to Anchorage, they use these gravels combined with brine. So have you studied anything with respect to the effect of gravel hitting the vehicles, and then it damages the vehicle like on that level, and then you have like salt, and then combination of those, and then what are the corrosion effects of those?
Mm-hmm. Well, in short, we haven't done any real tests, but based on my domain knowledge, that will basically make the things much worse because it could damage the coating, it could damage some of the protective layers we were talking about, and also once you induce a dent, that's where the local iron will start. So yeah, at every level, that's basically making things worse.
Yeah. So okay. Yeah, I just wanted to. Yeah, it's kind of like something came to my mind because the combination of the mechanical effects with respect to the electrochemical mechanism of corrosion, how that's going to work. Yeah.
Good point.
Thank you. It's a good presentation.
Thank you.
Any other questions? Well, all right then. Thank you very much, Dr. Shi, for the presentation. And just as a reminder, a copy of the presentation will be on the website later today or tomorrow, along with a recording of this webinar for others to watch. And on that note, thank you very much for attending, and hope you